and today's event is going to feature panel members from the Lcrd project, as well as the Space Technology Mission Directorate and the Technology Demonstration Missions Directorate as well. Just a few housekeeping things to keep in mind. If you need closed captioning, please hover over the video feed and you will see the CC button, which you can click for closed captioning. We will also have a live chat that is enabled on the right-hand side of the video for Q&A at the end of the event. If you don't see the chat feature right now, please change to a different browser or restart the current browser that you're in. Typically, we recommend Firefox or Google Chrome. Now I would like to introduce Georgie Brophy, the president of the Maryland Space Business Roundtable, to give opening remarks. Georgie?
Thank you so much, Bree. Hello, everyone, and welcome. I hope you're all healthy and safe and enjoying the start of this incredible summer weather in the DMV along with the cicada invasion. I am Georgie Brophy, Business Development Director of Space Systems at Nobles and the President of the Maryland Space Business Roundtable. The recent progress against COVID and the relaxing of related restrictions is very exciting. The MSBR board will continue to monitor the reopening of Maryland with the hopes of getting back to our in-person monthly luncheons and events soon, so stay tuned. Today, we are so happy to be partnering with Goddard to bring you a Goddard Engage Series event. The Engage Series started as a way to engage the Goddard community with Goddard's missions, projects, and various topics of interest. With this mission's launch slated for June 23rd, today's Engage session could not be more perfectly timed to feature a panel discussion on the past, present, and future of the Laser Communication Relay Demonstration Mission, or LCRD. During the panel, as Bree said, please join the conversation by submitting your questions via the chat box, and our MC, Dennis Farrick, Vice President, Corporate Strategy and Development at USRA, and our MSBR Director of Operations, will monitor and present the questions in our Q&A portion later. To kick things off, I'm honored to introduce Jim Reuter. Jim is the Associate Administrator for the Space Technology Mission Directorate at NASA headquarters, a position he's held since June 2019 after acting in this capacity since 2017. In this role, he provides executive leadership and management of the technology programs within the STMD. Jim came to headquarters from Marshall Space Flight Center and prior to that, Johnson Space Center after serving in a variety of senior executive and managerial roles, including technology and integration activities, space shuttle return to flight, and international space station efforts. Throughout his career, Jim has earned numerous awards, honors, and accolades at NASA. So we're honored to have Jim here today, and especially to share with us an overview of demonstration missions and why they're important before our panel kicks off. So Jim, over to you.
Yeah, thank you, Georgie. And I really appreciate the chance to be able to talk with you today and really look forward. Maybe we come back and get a little bit longer to discussion on what our mission directorate does, especially if we can do it in person. That would be so much. I'd be excited to see that day. We'll go ahead and go to the next chart, please. I just have a couple of charts that I want to talk about and give a brief overview of what we do in space technology and then how it relates to, as Georgie said, to why we do technology demonstration missions and especially the LaserCom relay demo that we're really excited to be at the verge of launching. And so this chart just depicts that our goal is to develop cross-cutting transformative technologies that can enable exploration and discoveries for both human and robotic missions, as well as really to help and anchor our space economy and the U.S. economy. And we do so as in a variety of programs that are really aligned along the technology development scale, from low TRL that are early stage, a concept stage, research grants to universities, some funding to centers, to mid-level stages, and then finally to tech demonstrations. We run the technology transfer program for the agency. We run small business innovative research for the agency. And we have a really exciting initiative that we call the Lunar Surface Innovation Initiative that is led for us just down the street from Goddard at Johns Hopkins APL. Today, we're going to talk about technology demonstration mission. One of our key ones is LaserCom Relay Demo. And so one last thing, I guess, is the key thing for us is there's a big transition that's required in order to go from a low technology readiness level to be able to work in the lab, and then another kind of valley of death, if you will, of going from something that's a mid technology level, working on the ground, to flying. And what we see is it's very hard to get new technology incorporated in missions unless you've actually demonstrated on flight, like we're about to do with Lcrd relay demo. So the next chart, please. I'll just say that the way we are organized, we have what we call a technology framework that we guides our investment strategies. We have 4 strategic thrusts for that, and they're listed across the top. Rapid, safe, and efficient space transportation, which we call GO. Expanded access to diverse surface destinations, which we call LAND. Sustainable living and working farther from Earth, which we call LIVE. And transformative missions and discoveries, which includes our laser comm demonstration, which we call Explore. So if you want to know what's our investment strategy, it's Go, Land, Live, Explore. And so with those, we've developed outcomes that we want to achieve, and with the outcomes and capabilities that we want to develop, some of which are directly relatable to lunar surface and feeding onto Mars, and others, such as the next-gen avionics and communications in the upper left, are activities such as this one we have today that service globally. Next chart. And then this is just a hodgepodge of the types of things we do. I won't go over all of them, because the main purpose today is the laser comm relay demo panel, and I don't want to take away from them. But we'd love to talk some more about it as makes sense. There in the upper row, the third one over from the left is of course our laser comm relay demo, and we're looking forward to the launch in about a month. Right next to it, we have some flight opportunities, small suborbital flights, as well as small spacecraft, and we have actually over 25 of those flights planned for this year. We're very proud of our participation in the Mars 2020 Perseverance mission, and we contributed 4 instruments, all of which have worked beautifully. Terrain relative navigation was the critical function that was kind of the eyes of helping Perseverance land in the Jezero crater among a lot of hazards and do so safely. META is a weather station that's been instrumental in its use of gauging the weather, dust, radiation, temperatures, and so on, and it's actually helped in terms of guiding the flight planning for the Ingenuity helicopter. And then also MOXIE, the instrument that we call MOXIE, has now successfully generated oxygen from the atmosphere of Mars a couple of times. It's working beautifully. Other technologies, if you go over more to the left, robotic refueling mission 3, and really with that, the OSAM, just below the Mars Perseverance, we have these OSAM-1 and OSAM-2 missions. What OSAM stands for is on-orbit servicing, assembly, and manufacturing, and we have 2 demonstration missions. The first mission is our most complex mission, as led by the Goddard Space Flight Center, doing an excellent job here as they have done with the laser comm relay demo. And so it's a flight plan for around 2025, where we would actually service satellites, refuel, assemble do another step where we assemble an antenna, and then actually do an on-orbit demonstration of manufacturing as well. OSAM-2 is a similar, smaller demo, but basically to demonstrate assembling and manufacturing of a solar array in space. Over farther to the left on the second column, I'll just point out the capstone mission, which is actually a 12U small spacecraft, the CubeSat, that will go into what we call the near rectilinear halo orbit, which is where we intend to fly Gateway. So it'll be the first. That's a very great orbit for us for enabling Artemis, but we've never actually operated that orbit, and so this will be a good early demonstration. And then finally, I think a couple of things. The Prime 1 right there in the middle, we have a lot of demonstrations that are planned for the commercial lunar payload services, the CLIPS landers for the moon that we have in development, and several of them are depicted here. And then finally, in the lower right corner, Deep Space Optical Communications is a sister program, or project, if you will, with LaserComm, and it's manifested and planned for the Psyche launch, so it's a deep space version of it. And next. with that, I'll just say let's tune in on June 23rd, where we're looking forward to the LCRD launch as part of the STP-3 mission. And I'm really looking forward to the panel that's and their discussions coming up, which is, and I'll introduce the Trudy Kortes right now. She's the director of our technology demonstration missions for our Space Technology Mission Directorate, and she'll be chairing the panel today. So thank you very much.
Okay, thank you, Jim. Hi, everybody. My name's Trudy Kortes. As Jim said, I'm really excited to be here. LCRD is one of several premier projects that we have in the TDM portfolio, which is a program that does system level demonstrations in relevant environments in the TRL 5 through 8 range. And LCRD is the next project that we have slated for what we like to call its day in the sun, a little bit literally and figuratively next month from KSC. I have with me today three outstanding individuals who are experts in the technology as well as the mission itself. We're going to talk to you a little bit today about what is currently happening with LCRD, as well as discuss some future applications and missions and infusion paths, things like that. So first we have David Israel. Dave is the Exploration and Space Communications Projects Division Architect at Goddard Space Flight Center. But probably more importantly for this discussion today, Dave was one of the original proposers of LCRD and has served as the principal investigator for this project since inception. So Dave's with us today. Javier Ocasio-Perez is also here from the project, and he is LCRD's Mission Integration and Test Manager. And then finally, Kendall Mauldin is the Technology, Enterprise, and Mission Pathfinder Office Chief, and he is here today with all kinds of information about LCRD's Experimenters program, which he'll describe later. So let's see, if you could, Brianna, roll the video, please.
Everything's fine. What you know is okay.
So, you know, I'll just say this is one of the first events we're doing that to get geared up for the launch next month. So just to see that is very exciting, and to imagine what that's going to look like on orbit. So Dave, let's start with you. First of all, just to set the stage for all of us, if you could explain a little bit about what optical communications is, why it's important, and then if you could tell us just a little bit more about LCRD, why the mission itself is important in furthering our technology advancements in optical communications. So let's start there if we could.
Sure. So hello everybody. It's great to be here. Excited with the launch coming up. So optical communications is the switch and the shift in our use of the electromagnetic spectrum. We're moving from radio waves to now light, infrared to be more specific. So we're transmitting over photons. So what that means, and it's the same principles as you know, fiber optic communications, you know, that people are familiar with here on Earth. So what that allows are really two things. The concentration of the power into that laser beam is what allows us to be able to get higher data rates with lower power, because your signal is all concentrated. And then also the physics allows our optical communication systems to be smaller for an equivalent data rate than if we tried to do it with radio waves in RF. So both those things, the increased data capacity and also the reduction in user swap size, weight, and power, make optical communications a key technology for future. So now to I guess the second part of the question was the importance of LCRD. So in 2013 there was the Lunar Laser Comm Demonstration Mission, LLCD, which was hugely successful and demonstrated 622 megabits per second from the moon and 20 megabits per second to the moon over laser, and that was a true technology demonstration mission. The first time showing that. It was highly successful. I like to joke, though, unfortunately, our ride was on the Laddie mission, which was designed on purpose to crash into the moon. So they took a perfectly functioning, excellent laser payload and crashed it into the moon on purpose. So we only had a limited number of hours to operate and demonstrate. So it was just prove the technology was what that did. So what the TDM mission allows is this getting an operational demonstration. As Jim referred to, some of these technologies are past maybe that technology demonstration, but there's still not the confidence yet for a variety of reasons for missions that want to be the first ones to use it. So having a TDM mission now gives us the chance to put Lcrd into a geo orbit with 2 optical terminals and get 2 years of operational experience, where we're going to understand the weather effects and how the service works, and really get to experience it when we're not counted on for an operational use, and we'll take everything that we learn to be ready then to apply this operational.
Okay, thanks, Dave. And no crashing involved on this one, so that's right. Good. That's right. No crashing. Yeah. Okay, very good. So Javier, let's bring you in. And so you oversee in your role, you oversee the integration and test of the payload. So tell us just where is Lcrd right now?
Yeah, so very exciting times. Lcrd, along with the STP-SAT-6 space vehicle, recently arrived at Astrotech in Florida. I'm here with part of the team. So that was earlier in May. After that, the space vehicle with Lcrd was transported inside the facilities. We connected all the hardware, the support equipment. And this last week, we just finished our final integrated system test, which basically verifies that all of the Lcrd interfaces and hardware connections are good to go before launch. And I'm happy to report that our system engineers and other team members agree that there's no need for additional testing before launching. So Lcrd is at this point ready to launch. There are still a few steps, obviously ahead of the launch, like we still have to install the spacecraft. We have to do additional testing at the space vehicle level. But from an Lcrd perspective, we're good to go for launch.
Okay, that's excellent. So can you describe in a little bit more detail, what's the process of getting, a payload or technology demonstration type of payload like Lcrd to, from that process of integration and test to the launch pad? Just give us some more detail about that, if you could.
Yeah, so I've been with Lcrd pretty much since the beginning, back in the day when the modems were being developed back at Goddard. So like Dave was mentioning, Lcrd was a technology that was first, developed by MIT Lincoln Labs. And then Goddard had the task to adapt it to be flown into space. And that was a big task into itself, right? So we had to adapt all the designs and then make it ready to start the INT process. So what do you do in order to get it ready, right? So we have a panel, a metal panel that our mechanical team put together, and then you install all of the boxes. We have different components like the space switching unit, optical modules, the modems. So all of them have to be installed, electrically checked out to make sure that they work. But the work doesn't stop there, right? After that, you have to functionally test all those components together, and that's where the challenges come in, right? Because one thing is when you do a design, and another thing is when you actually put it into practice. So that involves long hours of our team members being both on console and doing on-hands work to verify, for example, what is called data flows. The flows are the data that flows that's going to be demonstrated once we are in space. And just to give you an example, back when we were at Goddard, since we couldn't have the same distance in between, for example, the ground stations and the optical modules, we have specialized equipment like an optical test set table with special aligned mirrors that would mimic the distances. And that's how we, went through the process of verifying and validating all of the requirements. which culminated in a successful delivery of the payload last year in January 2020. And then we also finished recently the space vehicle INT campaign up to the point where we are now, where we're about to launch.
Interesting. That's interesting. I didn't know that about the mimicking of mirrors, but I do remember all of the hard work that went into the integration with MIT Lincoln Labs and them helping us with the specific technologies on the payload. So very interesting. Thank you. Okay, so Kendall, let's turn to you and bring you into this too for talk about some of the operations side of this. So clearly developing the payload and launching it, it's one step towards this, and Javier just talked to us a little bit about that. But there is a guest experimenters program to help us test out various scenarios. So can you tell us more about that and give us some more insights there?
Absolutely. So we're really excited, as you can see, that we're entering into this phase of the mission. And to speak to a little bit to your question about the experimenters program. So essentially, the way it's going to work is that, of course, the LCRD team will be checking out the payload after launch, making sure everything is working correctly, doing on-orbit checkouts, and that's all led by the operations team there at the Lcrd LMOC. And so what they'll be doing is making sure all the systems are working properly, both on the flight side and the ground side. And now after that period, which is estimated about 60 days after launch, once everything is checked out and everybody's comfortable that things are working properly, then we enter into what we call our experiment period. And that period is expected to be 2 years, minimum of 2 years, right there at that point of transition after the on-orbit checkout. So we expect that will probably start around September. And so once that period starts, basically we have several experiments that we will plan to execute. We have a team that's been working on preparing those experiments with various different experimenters. What's really exciting is the experimenters come from all different backgrounds and organizations. We have experimenters that come from internally within NASA. We also have some experimenters externally from NASA to NASA, from commercial industry, for example. We also encourage experimenters internationally as well as with other government. And so it is a wonderful opportunity for us to be able to see the variety of ideas that come from these experiments. So as we get ready to start the 2-year period, we are working with the operations team, which is a wonderful group of people. They've been working very hard getting ready for launch, but they're also getting ready for this 2-year period, which will be quite exciting to be able to execute these experiments during that 2-year period.
And you said they've already been selected and then they're getting ready to go.
Basically, yes. So there's a set of experiments that are being prepared now for the initial phases of the 2-year period. But as time goes on, we expect additional experiments to also be onboarded before and during the 2-year period. So we're looking forward to seeing a nice portfolio of various different types of experiments using the platform during that time.
Okay, so very good. So Kendall, let's stick with you for one more question, because as the office chief for Goddard's Tempo office, which I mentioned before, so how do you see what we're going to learn from LCRD playing into future missions and projects that might be in the formulation stage now? How do you see that this, us extrapolating what we learn here to that and then translating it there?
Absolutely. So what we see is very important for this mission, among many things, is as it's demonstrating the how you would operate an optical comm relay at GEO. What that opens up for us is we start looking at other future missions and opportunities that could make use of relay services, for example, as well as optical comm playing a big role in that relay service. And so we're really expecting we're going to be learning a lot as to how we would operate a relay and provide that relay service, as we also look to the future in how we would also utilize potentially commercially provided services, as well as government. And so this is really going to help inform some of the future developments as we're looking ahead to the horizon, as to how we operate the relay, but also how we can infuse optical communications into some future missions that may be looking to make use of the capabilities as they see this demonstration successfully executed.
Okay, thanks, Kendall. So Dave, back to you. Really very similar question, same question over to you. What benefits do you see optical communications bringing to future NASA missions? If you could talk about that for a little bit.
Sure. So it's the two categories in some cases combined is so the ability to achieve higher data rates, from anywhere. Even though we're sending LCRD at a geolocation, the biggest the two biggest challenges for the optical comm links from space to Earth. The first is the pointing requirements, so that gets different, the farther out you get. But the other major issue is going through the Earth's atmosphere. So once you're beyond the Earth's atmosphere, all that data that we collect and experience we get of dealing with atmospheric effects and weather will help all the future missions, so that we can put an optical comm link, any place and get those higher data rates. So whether it's future telescopes going to L1 or L2, or missions to Mars, once we want to do hundreds of megabits back to and from Mars, then optical is the only way to do it. And then for our small set cases, then maybe they don't want the huge data rates and data volume, but to carry a 2-centimeter telescope as opposed to a larger antenna, and a half-watt laser instead of higher power RF systems is a huge win for a small spacecraft as well.
So as we know, one of NASA's major priorities is building a sustainable lunar presence, and that involves infrastructure. So what are your thoughts on that? How could optical play into that, and what about that strong infrastructure that's needed?
Yeah, so we're working on we call it LunaNet, this network to support all the lunar activities. And a very direct analogy to the terrestrial internet is if you think of the transatlantic fibers and transpacific fibers, these optical connections that go between the continents that aggregate all the data coming from one continent and sends it to the other continent. So in the future, then we won't have the fiber, but we'll have the optical link, and we can have relays that are aggregating all of the traffic coming to and from the moon, and instead of having separate space links, we trunk them together and send them on an optical link to and from. So that's one benefit. Another interesting situation at the moon is that the far side of the moon is of great scientific interest, because you have the whole moon blocking all of the RF radiation and noise coming from the Earth. So for radio astronomers, especially, the far side of the moon is a great place to be. So we don't want to have RF relays flying and transmitting on the far side of the moon, because it'll ruin what everybody's excited about getting. So having optical links to get to and from the surface of the moon, just for those reasons, will be beneficial.
Okay, very good. Thanks. Far Side of the Moon. Not a bad Pink Floyd album. I mean, it's not my kind of music, but my husband really likes it. So there's that too. Okay, good to know. So Javier, back to you. So if you could talk a little bit about how was, in your experience, what made LCRD unique when it came to the building of the payload, and how was this different maybe than other missions that you have experience with?
Yeah, that's actually an excellent question. So earlier on, when LCRD was coming together, we were planned to fly in a particular spacecraft provider, but unfortunately that didn't work out. And at about the same time, we had a security component added to the LCRD requirements. And that was a big challenge for integration and test, which is my field, because typically at Goddard, all the missions that we've done do not really have a security component, meaning that you don't need personnel that need clearances, you don't need a special facility, put together to run a secure integration and test campaign. So what we did is that we had to convert a complete clean room area from a traditional, integration and test space to a secure one. And that involved from changing all of the locks, changing a roll-up door so that people couldn't like access it accidentally, from the outside. We had to modify feed-throughs so that only certain cables and harnesses could come in. It's even something like making sure people wouldn't spy or listen in, canceling, audio devices. It was pretty epic. And a downside to that was in integration and test, you always like to show the work that you're doing. We like to show pictures and how the LCRD was coming together. We were able to do that until a certain point before we started the flight campaign. At that point, we had to shut down all of the windows and people couldn't pick in due to the security. So that was something very different that we never done before. And LCRD was the first mission at NASA-Goddard to do a complete integration and test campaign in a secure environment. The other aspect that I want to talk about, which was peculiar to LCRD, right? Yes, we had the payload over at Goddard and we had a team there, but we also had a team at White Sands, New Mexico complex, which is where the operation teams is at. We have to work with them, hand in hand to get all the components together. We had our partners at JPL, right, that had the optical ground stations. We had to work with the Northrop Grumman spacecraft provider and also with the Air Force, who oversees the STP program that we're going to be part of. And that in itself is a huge challenge, right? Because you're not only having to manage a team at Goddard locally, but you're having also to manage expectations across the board, across the United States, in a lot of different institutions, and all of them with political ramifications. So it's been quite a journey, and I enjoyed it thoroughly.
Excellent. That sounds like interesting challenges that the team had, and it is fascinating how often things like communication and just integrating the people side of things are sometimes the most challenging parts of at least what I see in our TDMs. Very, very challenging. Thanks, Javier. So Kendall, back to you. So what's next on the horizon to really get to a point of operational optical communications? What would you say is next?
Sure. Yeah, so what's very, very exciting right now is to see the number of missions that are needing or requiring something we call high performance links. And there's various reasons that they may require that capability, but many times it comes down to data volume or data efficiency or other efficiencies that their mission needs to make use of, as well as spacecraft keep getting smaller. We see, the requirements for space, weight, and power, volume, all of it starting to get smaller and smaller as we see CubeSats and small sats and constellations of small sats, and even constellations of larger spacecraft that they're looking to communicate with each other within the constellation, for example, and they're looking for things like crosslinks between these spacecraft. So one of the exciting things that we see as we're engaging with some of these future missions, some of them are near future, some of them are far future. We are starting to see such a wonderful combination of requirements and what we call capability pull, from these missions to say they need this technology, they need this capability, and it's for a variety of reasons, but the need is very real. So there's a lot of eyes right now on LCRD for that reason, right? We want to make sure that the demonstration is successful, that we complete that experiment period, and that we're able to show, to the community at large, some of the use cases of through which you can use optical comm within the realm of LCRD. But there are other missions coming alongside, as Jim shared earlier, that are happening in parallel to demonstrate these capabilities, like the deep space capabilities that he spoke of. So many of these areas, what we're seeing now essentially is missions now coming to the realization of what the high performance needs. And when we start seeing that, we're able to connect the dots with some very real technologies that have matured for quite a while. And commercial industry has been working on solutions for quite a while as well for flight terminals, for example. So things have come a long way. And because of that, now we're able to connect those dots as we're looking at those future user needs, what the technology and capability pulls are from the user missions, and then be able to turn our eyes towards our operational networks, towards how we're infusing this into operational capabilities, as you mentioned, and making sure that we phase it early enough, right, that these capabilities are going to be available for some of the major missions and multiple missions coming up that can certainly use it and require it. So a big part, just to wrap that up, I think is a very good question. We see a lot of different potential uses on the horizon. As Dave spoke of earlier, the high performance trunk links, similar to those undersea cables that we have today on Earth, going between continents. We also see applications where, shorter distance crosslinks between spacecraft could be used. We see, as was mentioned, some lunar examples as well, or beyond. And so as we start seeing now those distances increase, especially as we start looking towards Mars and beyond, optical starts playing a very big role as we start seeing the efficiencies of counting individual photons to actually communicate data over very long distances. And so with that, we're excited to see what's happening here in the future, and to see what's happening right now in parallel with LCRD that's going to enable these capabilities and enable missions to get better science from their mission, to get real-time data, to get raw data down as opposed to compressed data. So there's also, and I think Dave would like to share something too here coming up as some of the missions that are coming up. But that's just a summary. There's lots of examples. High performance links are becoming more and more common in their needs. So I'd like to give Dave just an opportunity to share anything that he'd like to add.
Thanks. I was meaning to jump in. I just wanted to make sure that we mentioned that LCRD is not the only mission that's currently in this stage of development at Goddard. There's a terminal we call Illumity, which is going to fly to the space station, and that will be the first orbital user of LCRD. So when that gets connected onto the space station, then LCRD, which in the beginning will just be relaying data between our two ground stations, but then we'll have an orbiting user, and the goal is to then take that capability beyond just demonstration and start to provide real data services to the space station. And then there's also on the Orion Artemis 2 mission, there's a payload or mission we call 020, which will be an optical terminal flying on Orion to provide higher data rate links for Orion. So that's in order to provide that bandwidth for HD video to come back from the moon.
Okay, very good. And I just want to say something. We're going to go to questions here in a minute. And so I have one more question for everybody. But before we do that, I just want to say I would be remiss if I didn't mention the excellent partnership that space technology has had with the SCAN program, Space Communications and Navigation program within the Human Exploration Operations Mission Directorate. They've been a really great partner with us on several projects now, not just laser communication, but the Deep Space Optical Communication project that Jim mentioned at the beginning, Deep Space Atomic Clock that is currently flying now and in orbit until this fall. So they've been a really great partner with us for this. So I'm going to throw one last question out there to the panel, and I'm going to leave this open to anybody who would like to jump in and answer it. So how will optical communications benefit the general public? You know, NASA likes to tout spin-offs all the time, and how things we develop for space operations have terrestrial applications. We like to say that all the time. Can you relate LCRD benefits to some real life examples? So I'm not sure who wants to try that one.
I'll take a first cut at the answer. So one thing is there's they call them gateways for like satellite communications providers, the SATCOM industry will have a place where all the data gathers, and then they send it up to their satellite for then distribution. So they're hitting their bandwidth limitations too. So one of the things is to have that gateway ground station that they have to be an optical link. But there they have the challenge that they want that higher bandwidth, but they can't afford really to have outages due to weather and atmospheric effects. So our collecting of the data and characterizing how this will perform to GEO will be directly applicable to that application. So I don't expect that everybody's going to have an optical terminal on their house, because even if the costs are down, it's just not practical from a weather point of view. But I think where it will start to get into those systems is that the provider will have these high rate trunk lines up to their spacecraft, and then it'll go on RF to the public.
I don't know if it would help our wireless and my kids not complain about their phone service. I will pay any amount of money to have some kind of optical terminal on my house. I'm just saying that could be a great moneymaker. There's some commercialization there. Anyway, anyone else want to take a stab at that?
So Trudy, I just wanted to give an example that maybe might be more familiar with folks. So folks recently saw Perseverance, right? That landed on Mars. And it's going to be getting samples that are going to be returned to Earth. People noticed that the video and the images of the landing were not instantaneous, right? We had to wait to get those. Imagine when we have the technology of LCRD operational, and then we're sending humans to Mars, and then we're going to get the data instantaneously. We need to know that they're alive and that they're doing well. I'm going to go even further. Imagine when we're at some point going to go outside of the Earth to live in other places, and then we don't have to worry about the weather constraints on Earth. We're going to have high data internet via laser communication like LCRD, for example. So there's a lot, that you can keep going just with imagination, and yeah, it's exciting.
Yeah, that's a good point, and a way to bring in the recent Perseverance, all those successes that have been happening in Mars 2020 and that landing. So, okay, very good. Thanks to all of you. Excellent insights that you gave us there on the mission and the technology. So I'm going to turn it over now to Dennis Ferrick. Dennis is going to see if our audience who's with us today have any questions that we've not covered yet and they'd like answered. So Dennis.
Great. Well, thank you so much, Trudy, and all the panelists. We've got about 15 questions in about 15 minutes, so we'll do a little bit of a rapid fire round. Everybody can just jump in as I ask them. I'll try to be brief on my side. And thanks to the audience for the great questions. If they've been answered before, just let me know. I'm going to ask them anyway. Are there plans to launch relay satellites for use in deep space exploration, human travel to Mars?
So yes, so certainly relays will provide higher data rates and more continuous coverage. So it's the only question is when is it going to happen? But yes, it will happen.
Great. Next, on these small spacecraft opportunities, are you planning to have any platform similar to ESA OPSAT that allow small businesses to run experiments on a satellite?
Yeah, I guess I'll take that one. So actually, it's a really good question. And one thing I would mention is even on LCRD, we expect having opportunities for small businesses or really any experimenters that are interested in proposing an experiment idea can bring the idea to the table. And so one of the nice things about the experimenter program is it does open it up to commercial industry as well as international. And so industry is welcome to bring ideas, and then of course interacting with our group, we're able to take a look at what they want to do and see what's possible. I'm sure there's going to be, I would hope, future opportunities as well, but the opportunity is here now.
Yeah, there is a guest experimenter program is a component of LCRD. So the information of how to propose experiments is on our website, or people can contact me or contact us to find out more.
Great, thanks. Now, this is beyond LCRD, but an interesting question. I'll see if any technologists have thoughts on it. What is NASA doing to lower emissions from rockets to better protect the environment?
Yeah, it's not one I'm able to answer.
So I can't speak to large-scale launch vehicles, but TDM just did complete a green propellant infusion mission with some smaller in-space thrusters that use a non-hydrazine system and a monopropellant that the Air Force actually developed and has lower toxicity, easier for hazardous operations on the launch pad for loading and things like that. So can't speak to the larger scale, but on a smaller scale, in concert with Ball Aerospace and Aerojet Rocketdyne, we just completed that mission last year called the Green Propellant Infusion Mission. And whomever asked that question is welcome to go to our website, and we have much more information about it there and what that accomplished.
Great, thanks, Trudy. Laser comms currently at TRL 9, is that correct? Given the atmospheric transmission windows, why an IR laser and what wavelength?
So I guess the TRL 9 is TRL is sort of in the eye of the beholder kind of thing, right? So I would say that the thing that is not TRL 9, there are lots of our system that has been proven before, but doing through the Earth's atmosphere, it's really that space to ground link piece is the demonstration that's not really at a TRL 9 yet, I would say. Certainly we see commercial applications now, like Starlink came out and described how they're using optical links to connect space to space links between their platforms. So optical is getting operational in those cases, but so there's still more to prove for our case.
Great, thank you. What atmospheric monitoring is in place? Will it be solely located on the ground? Will transmissions to one site versus the other be planned ahead based on weather predictions?
So we do have instrumentation at both of our ground stations, and so the thing is, because we're not required to be delivering operational data, there's going to be periods of time where we're going to continue to transmit even when things aren't going so well with the atmosphere, just to characterize it. So we'll be scheduling events, based on our plans and our schedules, and depending on the experiment, there might be times where we intentionally ride through the atmospheric effects just to see how bad it gets, and then that will inform later experiments where we take a stab at seeing how well we're able to predict when we need to hand over, and then doing those handovers. So those will be all things that will inform our future operational planning, so that when we're supporting the operational missions, with Lunar or whatever they may be, then we'll be able to schedule it and operate and minimize any losses of data due to atmospheric or weather effects.
Okay, thanks. More on the operational lifetime. What are the limits on operational lifetime? How long would a system be expected to be operational? Are there servicing, replacement, maintenance costs expected for a system? And what happens after the experimental period?
Go ahead.
I was just going to chime in a little bit from the INT perspective, right? While we were doing INT, sometimes you have failures in the hardware, and of course, while you are on ground before launching, you have the opportunity, right, to rebuild and reinstall. One of the examples was on the flight modems. We had a flaw that we had to remove one of the towers, and then we discovered that the issue was in the other tower as well. So they both were removed, they were reworked, they had to go to environmental tests, and then they were reinstalled. So that is at the ground. Whether we can do that when we're in space, I mean, that would be a challenge for sure. And I don't know if Kendall or Dave want to talk more about what's after what could happen after LCRD.
Sure. Yeah, I guess one other thing I would add to Javier is you know, I won't speak to like serviceability per se once we're on orbit, but one of the things that has been a goal and requirement on LCRD is that the mission itself will last longer, is expected to last longer than the 2-year experiment period. And so we do expect there to be an extended portion of the mission. And of course, that depends upon, you know, environments. It depends upon life of components and things of that nature. But in a goal or in a requirement to make sure that we get some of that extended mission time, there's been quite a bit of effort invested in the reliability of the payload and the systems to ensure that we do get that extended mission time. And of course, you know, time will tell as to how long that extended time is. But as we know, we've seen many examples where spacecraft live longer than their minimum requirements. So we're looking forward to seeing what happens with LCRD.
Great. I've grouped a bunch of questions around the transmit receive, so I'll start to ask those in rapid fire here as well. Is it possible to test optical transmit receive equipment that's currently under development with LCRD system?
Yes, it is. So that is the type of experiment that we can support. Of course, it have to be compatible with our system. So that's the sort of thing. If people contact us through, I think they're going to post the addresses to contact us. Then we can start those conversations to explore what might be possible. Great.
And will the system be capable to aggregate RF transmissions into an optical feed?
So our system does have an RF trunk line to White Sands besides our 2 links to the ground stations. So in our case, yes, we can take data, send it RF up to LCRD, and then send it through our optical links or in reverse. And the number of links and how that's done is specific to our design, but some of our experiments are to kind of characterize and understand how you do that operationally to then expand upon that in the future.
Thanks. And what are the uplink and downlink speeds you aim to achieve with LCRD, and what's the target launch time on June 23rd?
Somebody else want to take a turn? I'm jumping on all.
Sure, I'll take
I believe the target launch time is late morning. I want to say, 10 or 11 a.m. It was 4 a.m. a little bit ago, and I think they've changed that to save us all. So I think it's 10 or 11 a.m. I've lost lock on which time it is now, but it's late morning.
Yeah, I heard morning, but I didn't have a specific time frame yet. Yeah.
We're all going to have our coffee ready to go that morning. And as far as data rates go, the highest data rates that we're expecting to accomplish as far as effective user data rates through the system is about 1.2 gigabits per second. So you can imagine during a full day how much data that we would be looking to transfer through the relay. So we're excited about that.
Yeah, and that data rate is not anywhere near the limit of what's possible with optical links. It was sort of based on the available technology and what we had at the time to implement this mission. All right, but the data rate is high enough for us to do the demonstrations. But everything that we learn about all the atmospheric effects and things with our signal will apply whether we're sending 10 gigabits per second or 100 gigabits per second through that circuit, that line.
And Dennis, before you go on, since somebody brought up launch, it just reminded me to mention, this is a U.S. Space Force launch, and that's another partnership that's been really great for us in this project. And this is their space test program. And in 2019, we launched 2 payloads with them as part of their space test program, and that's the Green Propellant mission I mentioned before, and Deep Space Atomic Clock. Those 2 payloads went up on that in June of 2019. So now we are here almost 2 years later, almost to the date, and we're getting ready to launch with them again. So this is a U.S. Space Force launch, and I just wanted to mention that to make sure people are aware.
Great. Excited to see the collaboration continuing. Regarding the receivers, how off the shelf are the receiving stations? What part of the day is lost due to the need to avoid sun illuminating the optics?
There's not that much. I don't know the exact number, but avoiding the sun, there is a minimum sun angle that's there, but it's a much smaller portion of the day than one would expect, just the way that the structures are built. And I'm sorry, I don't have a specific number for that. And then I forget, what was the other part of that question there?
How off the shelf are the receiving stations?
So the telescope itself can be more off the shelf, and in fact we're looking at building terminals where it's like a high-end home astronomer kind of 60 centimeter telescope could be used. It's really the expense is in the modem, the modems itself, and the coding and decoding. So that's certainly not off the shelf yet.
Okay, thank you. How will you determine if Lcrd has been a successful test?
So, I mean, obviously, after we launch, when we launch, we're not going to be powered on. We have to wait a little bit until then we can activate and deploy the lashes in the optical modules. So after we do that, the mission operations team is going to take over that process of activating, and then we'll do similar tests like we did during the integration and test campaign, right? So we already tested before launching all the different combinations of the data flows. Like Dave was saying, we not only do optical communications, but we also do high rate RF communications, which is also important because if for any reason you have like a weather constraint, you can go to the RF path and still do high rate data, and we also have we can encrypt that data as well. So we're going to follow similar processes as we did when we were in ground doing the testing. When we operate, one of the key differences though is that instead of having it in the ground, you have the full mission operations team, and then you also have integration team members in standby and payload subject matter experts to provide support as needed.
Yeah. So for the success, officially we have our success criteria, which are minimum experiments in the first 6 months to do. For me personally, the success that I'm looking forward to is when there's operational systems, either commercial providers or NASA systems that are being specified and built and operated based on the data that we get through our experience we get from our mission.
Okay, great. I've got one more question. That'll do some closing comments. With this last question, if anybody had anything they wanted to add for any other comments or clarifications, please jump in as well. Is there a method to peak the pointing if original pointing angles are off?
You guys want me? So yeah. So there is so pointing acquisition and tracking is a whole. It requires an algorithm and a beacon signal that comes from the ground station, and then the spacecraft finds it, and the two terminals find each other and then track each other. So there is an involved process to do it. In fact, when LLCD was about to launch, there were still people thinking that this thing out at the moon, orbiting the moon and back to the Earth with such a narrow beam, it will spend all its time trying to find each other, and then it will disappear behind the moon. And in fact, what happened was that it was so rapid, under a second every time to find each other that it proved that that pointing acquisition and tracking can be done.
Great, good to know. Well, thanks to everybody for attending, and especially our panelists and NASA and Goddard Communications for organizing this event. Maryland Space Business Roundtable looks forward to more joint events with Goddard Engage to include a focus on Wallops launches, and a big shout out to their launch last week, and another one coming, the NASA one last week, another one coming with NRO in June, and Landsat in coming months for these seminars. And in closing, appreciation for STMD for all their work on this and all the topics mentioned earlier. And for all of us, I really liked Jim's discussion of the STMD mission, and I think we'll all adopt it this summer. So go land, live, and explore. And best of luck with the launch this summer, team. Thank you so much. Bye.
Thank you.